Hello, welcome to the NPTEL online certification course on deep learning. You remember that in the previous lecture, we have talked about the feature distribution in the feature vector space, and we have shown that this distribution, because the different objects that we get from the same class, all of them may not be identical. The reason that they may not be identical is that the variation among the objects, whether it is shape or color or texture or illumination or orientation, whatever. So, when you get multiple instances of the objects belonging to the same class, it is hardly possible that the feature vectors that we compute given two instances of the objects belonging to the same class, those feature vectors will be identical. And because of this variation, when I have large number of objects belonging to a particular class and I compute the feature vectors of all those different objects belonging to the same class, all these feature vectors are not identical. Rather, in the feature space, they will form a sort of distribution. So, in today's class, in the previous class, what we have talked about this feature space representation, then we have talked about the Bayes rule, and then we have also talked about the Bayes minimum error classifier. So, today we will further analyze the remaining part of Bayes minimum error classifier, then we will go to what is known as Bayes minimum risk classifier, and I will also try to discuss whether there is any relation between Bayes minimum error classifier and Bayes minimum risk classifier. We will try to see that. So, this is what we have shown in the previous class, that is given images from the same class, but multiple number of images belonging to the same class over here. So, we had considered three different classes, the class of birds, the class of dogs and the class of cars. You find that all these representations of these objects in the feature space, that forms a cluster or a distribution. So, we had shown in the other figure in 3D how this distribution looks like, and we have said that because we are computing the distribution of the feature vectors belong from objects belonging to a particular class. So, this tells us what is the class conditional probability density function, or P of x given omega I, where omega I is the class and x is the feature vector that we have computed. So, experimentally, by collecting large number of objects from different classes, I compute this P of x given omega I. And at the same time, I also have an a priori probability, that is, what is the probability of occurrence of class omega I. So, I have two concepts, P of x given omega I and the a priori probability P of omega I, and from this, for classification or for recognition, what I have to compute is what is P of omega I given x. And we have shown using Bayes rule that this is nothing but P of x given omega I into a priori probability omega I. So, given two classes, say birds and cars, I have to compute, given an unknown feature vector, what is P of say car given x, and I also have to compute the probability of what is P of bird given the same x. And this P of car given x is nothing but P of x given car, which we have already computed through experiments, that is our class conditional probability density, multiplied by the a priori probability, what is P of car. Similarly, in this case, we will compute what is P of x given bird into a priori probability, what is P of bird. So, these are my class conditional probability densities, these are the a priori probabilities, and from this we compute the a posteriori probability P of car given x and P of bird given x. So, out of these two, whichever is more for a given unknown x which are vector. So, if I find that P of car given x is greater than P of bird given x, then my inference will be that this feature vector x belongs to car, or the object from which this feature vector x has been computed, that object is nothing but a car, nothing but a car. So, what we are computing is P of omega I given x, if it is greater than P of omega j given x, then my interpretation is x belongs to omega I. If P of omega j given x is greater than P of omega I given x, then my interpretation will be the otherwise, that is x belongs to omega j. Now, even in this case, you find that if I plot these two in one dimension, say P of omega I given x, maybe I plot something like this. So, here what I have is my feature vector x, and in this direction what I have is P of omega I given x. So, if my omega I is barred, then I can have this sort of a posteriori probability density, whereas for car maybe P of car given x is having some density something like this. So, this is my say omega I, this is my omega j. So, given any unknown x, say x vector is somewhere over here, you find that for this x, P of car given x is more than P of bird given x. So, as a result, I am deciding that this x belongs to car, it does not belong to bird. But still there is a finite probability that x may belong to bird also, and that is what is my probability of error. So, in this case, what is the probability of error that I have? The probability of error is nothing but the minimum of the two. So, P error, if I put it, write it like this, P of error given x is nothing but minimum of P of omega I given x and P of omega j given x. So, as I am taking the decision which minimizes the error, because it is minimum of these two quantities P of omega I given x and P of omega j given x. So, the classifier that we design is what is known as Bayes minimum error classifier. And what is the total error in this case? Total error of classification is nothing but the error or the area under this curve. So, which is nothing but if I integrate this area minimum of these two over x varying from minus infinity to infinity, then what I get is the total error of this classification rule, that is given by this minimum error classifier. Okay. Given this, now I go to the next type of classifier, which is Bayes minimum risk classifier. So, Bayes minimum risk classifier is more general from Bayes minimum error classifier, in the sense that in case of Bayes minimum error classifier, we have considered only the classes. Say if I have C number of classes, then I have classes omega I varying from 1 to C. So, if I take c number of classes omega I, where this I varies from 1 to c, if I have c number of classes. In case of Bayes minimum risk classifier, we consider this omega I to be the states of nature, which are nothing but classes for our classification problem, and we also have a set of actions, say alpha I, where, or alpha j, set of actions alpha j, where j varies from say 1 to capital K. So, I have c number of true states of nature, I have k number of actions alpha I. As before, I consider the feature x to be a d-dimensional feature vector. But what makes Bayes minimum risk classifier more general than Bayes minimum error classifier is introduction of a loss function. So, this loss function is introduced, loss function lambda, which is alpha I given omega j. That means, if I take an action alpha I, where the true state of nature is omega j, or the true class is omega j, then the loss that we incur is lambda alpha I given omega j. So, given this, the Bayes minimum risk classifier works in this fashion. In our classification problem, our problem is that given an unknown feature vector x, we told earlier that any input signal now will consider to be a feature vector in my feature space. So, my classification problem is that given any unknown feature vector x, I have to compute, or I have to predict to which class omega I that feature vector belongs. So, that is my classification problem. So, in case of Bayes minimum risk classifier, it is assumed that for every such action you take, or for every such prediction that x belongs to a particular class, you have a risk involved in it. So, you compute the risk, the value of the risk for every decision that you are taking, and the decision that gives you the minimum risk, you have to take the corresponding decision. So, it is like this. So, again I assume that I have a given feature vector x, and on this x I take an action alpha I. So, the risk involved in taking action alpha I given x can be computed as, if the true state of nature is say omega j, then we said that we incur a loss lambda alpha I given omega j, because alpha I is the action that I am taking, whereas true state of nature is omega j, it should have been omega j. So, while taking this action, I incur some loss. So, that is my loss function lambda omega I given lambda alpha I given omega j into what is the probability p of, sorry, let me rewrite. So, I have been given vector x and I take an action alpha I. So, I compute the risk r of alpha I given x, which is nothing but the risk involved for taking action alpha I if the true state of nature is omega j multiplied by a posteriori probability p of omega j given x, and you take the sum of this over all j. Why over all j? Because I am taking action alpha I, maybe the actual the true state of nature is omega 1, the signal actually belongs to class omega 1. So, for that what is the risk? It may actually belong to class omega 2, for that what is the risk? and likewise it may actually belong to class omega c, and therefore for that what is the risk. And if I add all these risks, then I get the overall risk for taking action alpha I given my feature vector x, right. So, this I have to take. So, I have to compute this R of alpha I given x for all I. We said that we have k number of actions. So, for all I varying from 1 to k, and out of all these, for whichever R of alpha I given x is minimum, I have to take that corresponding action. So, that is why it is Bayes minimum risk classification. That is, I want to take that particular action for which my risk is minimum. Unlike in case of Bayes minimum error classification, there you decided x to belong to a particular class which minimized your error. So, now it is minimization of risk. Now, let us see whether I can establish any relation between this minimum risk classification and minimum error classification. Let us assume that we have an 1 0 loss function. That is, I assume that lambda alpha I given omega j, let me represent this in short as lambda I j. So, if I is equal to j, that means I am taking the correct action. It belongs to class omega j, and I am saying that, and my decision is it belongs to class omega j, and it actually belongs to class omega j. So, in that case, the loss function, the loss that I incur is 0. So, I assume that this lambda, the loss function, is equal to 0 if I is equal to j, and I also assume that this is equal to 1 if I is not equal to j. So, that is for every incorrect action you incorporate a unity loss, and which is same for all incorrect decisions. But if your decision is correct, obviously you are not incurring any loss. So, lambda I j is equal to 0. So, given this, now if I compute the risk involved in taking an action alpha I given x, which we have said that this is nothing but lambda I j, that is lambda of alpha I given omega j into p of omega j given x, and sum of this over all j. And now taking these values of lambda I j, you find that we have defined that wherever I is equal to j, lambda I j is equal to 0, and wherever I is not equal to j, lambda I j is equal to 1. So, this expression simply becomes p of omega j given x, take the summation over all j not equal to I, because wherever j is not equal to I, lambda I j is 1, and whenever j is equal to I, lambda I j is equal to 0. So, I have to take this summation over all j where j is not equal to I. For all of them, lambda I j is 1, and this is nothing but 1 minus p of omega I given x. Now, see that what we wanted is in Bayes minimum risk classification, I want to take that particular action alpha I for which R of alpha I x, alpha I given x is minimum. In Bayes minimum risk classification, we wanted to classify x to that particular class for which p of omega I given x is maximum. Now, if you look at this expression, that R of alpha I given x is equal to 1 minus p of omega I given x. Obviously, you can find out you can check that r of alpha I given x will be maximum or r of alpha I given x will be minimum when p of omega I x is maximum, because r of alpha I given x is nothing but 1 minus p of omega I given x. So, wherever r of alpha I x is minimum, p of omega I given x is maximum. So, in this particular case, when my loss function is 1 0 loss function or 0 1 loss function, that is for every correct decision, I assume that I incur a loss or I do not incur any loss, that is the loss function value is 0. For every incorrect decision, I incur unity loss. So, under that condition, my Bayes minimum risk classifier and Bayes minimum error classifier, both of them are same. But in general, for taking wrong decisions, for different types of wrong decisions, my loss function will not be same. Right. So, we will discuss about that more later. Now, let us consider a case of two classes. So, we are discussing about the risk function, and we have defined that if you take an action say alpha I, where the true state of nature is say omega j, then for an given input vector x, the risk involved is given by r of alpha I given x, which is nothing but lambda alpha I given omega j into p of omega j given x, and you take the sum of this over all j. So, that is the total risk for taking an action alpha I given an input feature vector x. So, if I have say k number of such actions where alpha I varying from 1 to k. So, for each of this I have to compute what is the risk function, and I have to take that particular action for which the risk involved is minimum. So, that is what Bayes minimum risk classifier says. So, now let us take a two class problem where I assume that I have two actions given as alpha 1 and alpha 2, and I have two states of nature or two classes given by omega 1 and omega 2. So, let us try to find out that what is the risk involved if I take an action alpha I, or what is the risk involved if I take an action alpha 2. So, alpha 1 and alpha 2, I want to compute the two risk functions, and the loss function that we have defined lambda alpha I given omega j. For simplicity, I will write this in the form of lambda I j. So, the risk or the loss function for taking an action alpha I, if the true state of nature is omega j, which is lambda alpha I given omega j, I represent this as lambda I j. So, given this, now I will have two risk functions involved. One is for taking action alpha I, the other one is for taking action alpha j. So, I have to compute r of alpha 1 given omega 1, and I also have to compute r of alpha 2 given r of alpha 1 given x, and I also have to compute r of alpha 2 given x. So, this r of alpha 1 given x is nothing but lambda 1 1 p of omega 1 given x plus lambda 1 2 p of omega 2 given x. So, here you find that lambda 1 1 is nothing but lambda alpha 1 given omega 1. Similarly, lambda 1 2 is nothing but lambda alpha 1 given omega 2. And in the same form, I can write all of r of alpha 2 given x as lambda 2 1 p of omega 1 given x plus lambda 2 2 p of omega 2 given x. So, given these two risk values, my decision will be in favor of action alpha 1, or deciding that input x belongs to class omega 1 is when I find that r of alpha 1 given x is less than r of alpha 2 given x. That is, the risk involved in taking action alpha 1 is less than the risk involved in taking action alpha 2. So, if I put this, bringing or using the risk values from here, I have to have lambda 1 1 p omega 1 given x plus lambda 1 2 p omega 2 given x. This has to be less than lambda 2 1 p of omega 1 given x plus lambda 2 2 p of omega 2 given x. Or I can rewrite this as lambda 2 1 minus lambda 1 1 p of omega 1 given x has to be greater than lambda 1 2 minus lambda 2 2 p of omega 2 given x. Right. So, this is the condition that has to be satisfied, that is lambda 1 2 minus lambda 2 1 minus lambda 1 1 into p of omega 1 given x has to be greater than lambda 1 2 minus lambda 2 2 p of omega 2 given x. So, let me just rewrite this in the form as let me or refresh this. So, my condition was that lambda 1 1 p of omega 1 given x plus lambda 1 2 p of omega 2 given x, that has to be less than p lambda 2 1 p of omega 1 given x plus lambda 2 2 p of omega 2 given x. So, which we have rewritten in the form lambda 2 1 minus lambda 1 1 p of omega 1 given x has to be greater than lambda 1 2 minus lambda 2 2 into p of omega 2 given x. So, this is the condition that has to be satisfied for taking a decision in favor of class omega 1 or for taking action alpha 1. So, I can also rewrite this in the form p of omega 1 given x upon p of omega 2 given x to be greater than lambda 1 2 minus lambda 2 2 upon lambda 2 1 minus lambda 1 1. And you remember that lambda 1 2 is the loss function for taking an action alpha 1 when the actual true of nature is omega 2, and lambda 2 2 is the loss function involved when you are taking action alpha 2, when the true class of nature is omega 2. So, naturally lambda 2 2 has to be less than lambda 1 2. Similarly, lambda 1 1 will also be less than lambda 2 1. So, both these quantities, both in the numerator and denominator on the right hand side, both these quantities are positive. And again, you remember from the Bayes rule that p omega 1 given x, which is the a posteriori probability, I can write this as p of omega 1 given x as p of x given omega 1, which is the class conditional probability, into the a priori probability p of omega 1. Similarly, p of omega 2 given x can also be written as p of x given omega 2 into p of omega 2. So, using this, now this expression can be written as p of x given omega 1 upon p of x given omega 2 has to be greater than lambda 1 2 minus lambda 2 2 upon lambda 2 1 minus lambda 1 1 into p of omega 2 upon p of omega 1. So, now considering this p of x given omega 1 to be a function of omega 1, p of x given omega 1 gives me the likelihood value, and accordingly p of x given omega 1 upon p of x given omega 2, that gives me the likelihood ratio. So, this expression that in order to take an action in favor of class omega 1, which is p of x given omega 1 upon p of x given omega 2, has to be greater than lambda 1 2 minus lambda 2 2 upon lambda 2 1 minus lambda 1 1 into p of omega 2 given omega 1. This condition has to be true for taking an action in favor of class omega 1, and that is what comes from the Bayes minimum risk classification rule. So, going by that, you find that on the right hand side of this expression of this inequality, that is lambda 1 2 minus lambda 2 2 upon lambda 2 1 minus lambda 1 1 into p of omega 2 upon p of omega 1, this is independent of x. So, a favorable decision in favor of class omega 1 can be that if the likelihood ratio is greater than certain threshold, where the threshold is given by this. The thresholds are in terms of the loss functions and the a priori probabilities. So, we can say that if the likelihood ratio is above than this threshold, then we take an action in favor of class omega 1. So, we will continue this discussion further. So, in today's lecture, what we have discussed about, we have recapitulated our previous lectures content, that is feature representation of a given signal. Then we have talked about the Bayes theory and the Bayes minimum error classifier, Bayes minimum risk classifier, and we have also tried to establish that what is the relation between Bayes minimum error classification and Bayes minimum risk classification. Thank you.